In this video, we're going to talk about the regulation of gluconeogenesis. In this, I'm assuming you've seen my video on what gluconeogenesis is and also have some idea of glycogen and how glycogen regulation works. So I've got video on that as well. So if you haven't seen those, you might want to check them out. Otherwise, let's get into this. So how is gluconeogenesis regulated? So recall at a high level what gluconeogenesis is doing is it is producing glucose in the liver in response to low blood sugar. So if we have muscle cells are consuming a bunch of glucose, they're importing it from the bloodstream. The pancreas sends out the bat signal here saying blood sugar is going down, that's glucagon. So liver cells start exporting glucose from both glycogen and by gluconeogenesis. We're going to start as a model for how gluconeogenic regulation happens by looking at how glycogen regulation works. And so I'm going to disappear here. So quick reminder that phosphorylation leads to reciprocal regulation of glycogen production and breakdown. And so here I'm showing this central switch for glycogen being formed, which is saying store glucose as glycogen, and glycogen being broken down, which is make glucose for export, right? Those are the two possible things, at least in a liver cell. If the system is unphosphorylated, what that means is the PYG, the glycogen phosphorylase, which breaks down the glycogen, is off, and the glycogen synthase is on. So when it's unphosphorylated, it's saying store glycogen. But when things are phosphorylated, when we end up over here, what we activate is glycogen synthase. So phosphorylation, sorry, I said that backwards. So many things to keep track of here. Phosphorylation activates glucose for export, and it does so by activating glycogen phosphorylase and deactivating glycogen synthase, right? So this phosphorylation switches both saying break down glycogen and stop making glycogen. Okay, so we're going to keep that in our head because we're going to see something similar, but just different enough to be confusing when we're talking about glycolysis and gluconeogenesis. So inside of a liver cell, when we're running glycolysis, we're actually generally, there's some we're using for energy generation, but if we have high sugar around all the time, what we're actually going to do is route that glucose down to pyruvate, run glycolysis, and ultimately store it as fat. And so we can think about this when this is in the glycolysis state. What we're basically saying in a liver cell is store glucose as fat. This is glycolysis. And in future videos, we'll dig into the sort of the downstream stuff of glycolysis. But for now, just we can think about it. You got a lot of energy around, you're burning it, you're storing glucose as fat. You're converting glucose into fat. In contrast, if you're running gluconeogenesis, what you're doing, gluconeo, is you're making glucose specifically to export, right? And so that is like breaking down glycogen with glycogen phosphorylase. Now we're doing gluconeogenesis. The output is the same. We're making glucose in both cases. Okay, so again, glycolysis is store glucose in this case. Gluconeogenesis is export glucose. All right, so let's start unpacking it. The regulation for this looks pretty complicated, but it turns out it actually has the same fundamental logic that we've already seen. And so what I'd like to do is tease this apart to identify that logic. So here's our central switch again. We've got the switch between glycolysis going this way and gluconeogenesis going this way. Yeah. Oh, and actually, I meant to say this earlier. Sorry, I should have said it. PFK1, if you remember back to the glycolysis videos, this is that first step in glycolysis. This is that rate-limiting step. This is the faucet for glycolysis, right? So if we speed this up or slow this down, we're speeding up and slowing down the entire rate of glycolysis. So this is a really good step to regulate switching between glycolysis and gluconeogenesis. Okay, sorry, I should have said that earlier. Okay, let's start unpacking this switch. So this switch is actually built around this molecule here, fructose 2,6 bis phosphate. which I think is what makes it feel so confusing. There's this other random molecule going around. Fructose 2,6-bisphosphate is derived from fructose 6-phosphate. It actually looks a lot like a fructose 6-phosphate, so it's just one phosphate away from that. And this reaction of forming fructose 2,6-bisphosphate is catalyzed by this PFK2 enzyme, and the loss of that phosphate, the dephosphorylation, is catalyzed by this enzyme here, FBP2. Okay, let's see what happens. Let's actually look at the molecules and then we'll see how it happens. So this right here is the molecular structure of fructose 6-phosphate. This is fructose 1,6-bisphosphate, which is where the system is going to go if you turn on metabolism, turn on glycolysis. And this is fructose 2,6-bisphosphate, which I wrote over, but don't worry, we've got it in bigger over here. So this is fructose 1,6-bisphosphate. It is a glycolytic intermediate. We've seen it before, right? This is the step after fructose 6-phosphate. You put a phosphate on to make F16BP. F26BP is an allosteric signal. And you'll notice they differ only in the position of the phosphate. So fructose 1,6-bisphosphate has a phosphate on the 1 carbon, while fructose 2,6-bisphosphate has phosphate on the 2 carbon, right? Very difficult nomenclature. Okay, it's annoying to keep track of, but that's all that's different between these two is where that phosphate goes. But it turns out putting that phosphate in different places gives different molecular recognition rules and different physiological roles for these molecules. So let's start unpacking those. So if fructose 2,6-bisphosphate is high, glycolysis is active. And the reason for this is fructose 2,6-bisphosphate allosterically activates fructose phosphofructokinase, PFK1, and it allosterically inhibits FBP1. So basically it turns this off and it turns this on. And this is all allosteric, right? So it's not binding at the active site, it's binding elsewhere, and it's changing the conformation, changing the dynamics of the proteins, making PFK active, making FBP1 inactive, okay? So if F26-bisphosphate is high, glycolysis is active. If F26-bisphosphate, F26BP is low, gluconeogenesis is active. Why is that true? Well, this molecule is now no longer here, which means the activity of this molecule goes down. And this molecule is no longer here, it's no longer inhibiting activity, so the activity of this molecule goes up. So this one molecule, F26-bisphosphate, F26BP, depending on its presence, it's either turning on glycolysis or it's turning on gluconeogenesis, right? It does both things at the same time. All right. So what determines F26-bisphosphate levels, right? Phosphorylation. So this is where it should start ringing bells and making you think like, oh, I've kind of seen that before in say, glycogen signaling. So here is the pathway for the synthesis of these, but now we're going to start adding another layer. The first is, look at this. This had a phosphate lurking on there. Maybe you noticed that before. The phosphorylated form of FBP2 is active, and the dephosphorylated form is inactive. When this thing is phosphorylated, it is breaking down F26-bisphosphate. As a result, it is lowering the activity here, which lowers PFK1's activity and activates FBP1's activity. So it turns on, as when we phosphorylate the system, we're turning on gluconeogenesis. The flip side of this phosphorylation is we're also turning off PFK2. So we're not only triggering the breakdown of any existing pool of F26-bisphosphate, we're no longer making more. So the kinase comes in, it phosphorylates FBP2. That will break down any F26-bisphosphate that's around. It will inhibit the formation of new F26-bisphosphate. That will inhibit, or that will no longer activate PFK1, and that will no longer inhibit FBP1. So the net flow of this system is this direction. So many moving parts. But the opposite is also true. So now we're going to do dephosphorylation. And if you've been confused by this so far, maybe pause for a second and try to convince yourself of what's going to happen. What is the chain of events that will happen when you do dephosphorylate these two enzymes? And hopefully by understanding that, then you'll be in a good position to understand the other side too. So maybe pause if you want to and think about it. All right, here's what happens. So we dephosphorylate FBP2. That makes this inactive, which means we are no longer going to be breaking down F26-bisphosphate. When we dephosphorylate, this is now going to be active, meaning that we are going to start making more. We're going to increase our concentration of F26-bisphosphate. If the concentration of F26-bisphosphate goes up, we are going to activate PFK1, and we are going to inhibit, we're going to stop FBP2, which means that the net flow of this reaction is now going to flow in this direction, right? We have opened the kitchen faucet so that now glucose is flowing into pyruvate. We are now running glycolysis. So the same sort of switching logic we've seen in the past, where phosphorylation of two enzymes can switch the system from having a preference for one direction versus the other. So what determines phosphorylation? Signaling cascades, right? And we've seen this before. This is something I showed in a previous video, looking at how glycogen synthesis and breakdown responds to glucagon signaling, the low blood sugar signal, and insulin signaling, the high blood sugar signal. I should have written its name to be parallel. Insulin. And this is low sugar. And what glucagon does is it activates a kinase right here that does a lot of phosphorylation. And what insulin does is it activates a phosphatase here that does a bunch of dephosphorylation. So let's pull the core logic out. So we can say, we've got this kinase on the top, we've got a phosphorylase at the bottom. See exactly the same sort of thing in the regulation of gluconeogenesis, right? So we've got a kinase at the top that is saying, what is this one saying? Got to think about it. It is saying run. This is saying release glucose, right? That's what the kinase is saying, because it is putting this FBP2 into the active form, causing the breakdown of F26-bisphosphate, which relieves this inhibition and turns this off, which means that overall the system flows this way. We are releasing glucose. And we see the same thing here. When we activate the kinase for glucagon signaling, what we're going to do is we are going to activate glycogen phosphorylase, which is going to break down glycogen into glucose, right? So both of these signals say, let's make more glucose. When you turn on the kinase, make more glucose. And the opposite is also true, right? If you dephosphorylate, you flip the signal on both. In this case, you flip for glycogen, you switch to glycogen synthesis. And for gluconeogenesis and glycolysis, you switch to glycolysis. So the same signal activates gluconeogenesis and glycogen breakdown, right? If you have glucagon around, it's going to say both break down your liver glycogen and start synthesizing glucose, which makes a lot of sense, right? You have the same physiological output, the increase of glucose, that's regulated by the same signaling cascades. Okay, that was a lot, but hopefully we can pull out some big picture ideas. So first, gluconeogenesis and glycolysis are reciprocally regulated. So if one is on, the other's off. If one is off, the other's on, at least to a first approximation. This is mediated by the allosteric molecule F26-bisphosphate, or F26BP, which activates glycolysis and inhibits gluconeogenesis, at least in the liver. F26BP levels drop with phosphorylation and increase with phosphorylation of their particular enzymes, which means a signal that phosphorylates causes a drop in F26-bisphosphate and an increase in gluconeogenesis. This parallels the logic of glucose production from glycogen, so we can see how one set of signals can give rise to two parallel physiological responses. Okay, So that's what I have on that. Hopefully it was informative and not too chaotic. Hopefully you can see some of the big picture ideas of systems of regulation, even amongst all the details. Anyway, I hope you enjoyed that, and I will see you later.